We have been discussing about the lubrication theory, and we have come up with a set of simplified x and y momentum equations, where x and y are two orthogonal directions in the plane of the flow, where we have discarded some of the terms in the momentum equation, keeping in view that they are not important because of the order of magnitude of those terms relative to other more dominant terms. So, we will just reconstruct the physical situation that we were considering. So, an arbitrary top surface for which the height is a function of x and time, where these are the x and y axis. So, the x momentum equation for the gap height much smaller than the length will be 0, plus a forcing term, right, and y momentum plus a forcing term. The exact mathematical descriptions of these forcing terms we have discussed in the previous lecture. We will now consider an example where no such force exists, and that is why I have just generically included these as forcing term, because these we will set to 0 as the special case. So, before solving these equations we made a coordinate transformation. So, this okay, first of all here mu will not be there because these are all dimensionless versions, right, just check once, these are all dimensionless versions. So, mu will not be there, it is absorbed in one of the non-dimensional parameters. So, this h is a non-dimensional h which is a function of non-dimensional x and non-dimensional time. The boundary conditions, so we have considered a reference frame, this is having a non-dimensional velocity this one. So, this we are assuming that there is a reference frame that moves towards the right with a velocity u naught. So, with respect to that reference frame, so right means along x, moves along x with velocity u naught. So, if that be the case, then the boundary conditions are for this equation at y is equal to 0, u is equal to minus u0, and at y is equal to h, which is a function of x and t, u equal to 0. Okay. Now with this background, what we will do is we will solve this equation first to get a velocity profile. So if you integrate the x momentum equation, what you will get? Right. So when you are integrating this with respect to y, x is like a constant. So this could be a function of x and u is equal to so at y is equal to 0, u equal to minus u0. So this, let us call this boundary condition number 1 and this as boundary condition number 2. So boundary condition number 1, this will imply at y equal to 0, u is equal to minus u0 means C2 is minus u0, it becomes a constant. But you see this is a formulation where you have a provision of accommodating a velocity which is a function of x, right. Had u0 itself been a function of x, this could be a function of x, right. And the boundary condition 2 at y equal to h, u equal to 0. So 0 that means that C1 is u0 by h minus this one. So we can h by 2, right, h by 2. So the velocity profile becomes u is equal to 1 by 2 into the pressure gradient into y square minus yh plus u0 y by h minus 1, right. Whenever you get a solution, not just for fluid mechanics but for any problem, the first thing that you should check is whether it is satisfying the boundary condition. Not that if it satisfies boundary condition it is bound to be correct, but if it does not satisfy the boundary condition it cannot be correct, it is the other way around. So at y equal to 0, u is equal to minus u0 and at y equal to h, u equal to 0. So at least it satisfies the boundary condition. The y momentum equation does not come into the picture here because it trivially tells that pressure gradient along y is 0. So, you do not have to bother about pressure variation along y, you may have to bother if the body force along y is important, right. Here we are not considering any forcing term along x and y. So, here these are examples with forcing term equal to 0 that we have to keep in mind. Many nice problems can be generated from this general formulation by specifying different forcing terms. So, now what we will do is we will develop a strategy. What is our objective? Objective is to get a governing equation for pressure distribution. Why is pressure distribution so important? So, look at the pressure scale. If you recall the pressure scale, what was the pressure scale? Just tell me. PC. One of you just tell because it is difficult. Mu UCL by H naught square. So, this you can write in terms of the small parameter mu UC epsilon square L, right. So, PC scales with 1 by epsilon square, right, or varies with 1 by epsilon square, even forget about the other things, that it varies with 1 by epsilon square. But the other form of stress, that is the shear stress, tau is what is equal to mu into the velocity gradient. So, tau scales with what? Mu c into mu into UC by H naught, right. This is like mu du dy, scale of du dy is UC by H naught. So, this is of the order of mu UC by epsilon L, right. So, if you compare the effect of pressure and effect of shear, these scales with 1 by epsilon square and these scales with 1 by epsilon. Epsilon being small, the pressure is much more significant in lubrication theory than the hydrodynamic shear itself, and that is why the pressure distribution itself dictates what will be the force on the boundaries, and that is why we need to develop a governing equation for the pressure distribution, that is the objective. So, the strategy that we will follow is very simple. What is the strategy? We will differentiate this with respect to y. So, with respect to x, and equate that with minus of del v del y from the continuity equation. We will integrate that equation to get v, and v at y equal to h is nothing but del h del t, the rate of change of h with respect to time, that will close the problem. So, let me work out the steps, then you will understand it better. So, you have what will be the derivative of this with respect to x? We are using a product rule. First derivative of this with respect to x, this as a constant, then this, then derivative of this with respect to x. What will be this? Which term is a function of x here? H, right. So, what will be that? Right. And for the second term, this is nothing but equal to from the 2D incompressible condition. Okay. So, in principle if you integrate this with respect to y you will get v. Remember these are all partial integrations because this is a partial derivative. So, if you integrate this with respect to y, so you take minus half as common,
compressible equation was for u prime and v prime. So when we convert it to u and v,
it will
there will be some constants. There will come some constants.
in the leading order. In the leading order, let us check. So you have this one. So u is equal to u bar sorry what is that, u dash by u c, v is equal to v dash by v c, x equal to x dash by x c, and y sorry L, what here x c is L, and y is equal to y dash by h naught. u c and v c are chosen to satisfy this equation, right. So, because they are chosen to satisfy this equation, the relationship between u c and v c are such that when you substitute it, dimensional and non dimensional forms will be the same. Okay. So, then so this will be y cube by 3 minus y square by 2h then if I make any mistake just alert me, do not just blindly copy, you do it yourself and then check. Then next term is u naught y square by 2 this is minus u naught y square by 2 into 1 by h square. So, this plus C3 x. In principle v could be a function of t also, time also, right. So, this you may extend it to be a function of both x and time, but eventually you will get this as a constant value by satisfying the boundary condition. So, this is v. So, what boundary condition we will now substitute here? So, at y equal to 0 V is 0, this is that no penetration boundary condition. So, at y equal to 0, if you put V equal to 0, that means C3 will be 0, right. So, you will get an expression for V. So, you will get a governing equation for pressure if you substitute that at y equal to h, this is kinematic constraint, that is the rate of change of h with respect to time is the velocity at y equal to h, that has to be same as the velocity of the plate at y equal to h, otherwise there will be a lack of contact between the fluid and the plate and fluid have to move together, it is pure kinematics. So, then let us substitute minus half this is h cube by 3 minus h cube by 2. So, minus h cube by 6, then this is minus so, these two terms you can club together and write, let us utilize this space. So, this is the first term, and the second term you consider this is 3 h square by 12, that means h square by 4, these 2 and these 2 comes together. So, these two terms clubbed together is this, right. Okay.
Sir, is del H del T numerically equal to V0?
Yes, this is V0, this is V at y equal to h, this is equal to V0. With the coordinate transformation the x velocities have changed, y velocities have not changed. So, this is equal to V0. This is at y equal to h, V is V0, which is nothing but this one.
So, but if we fix an x value, so how the value will of h will change? It is given by del H del T, but that is not exactly the y.
This is kinematics. So, if you have two plates given you have a height, imagine a fixed height, if the top plate is moved with a velocity, what is that velocity? It is the rate of change of the h value located from the bottom, right, rate of change of that with respect to time. So, that is what it is.
So, but we have a finite u0 as well.
U does not, u0 is not finite, that is what this has become 0 because of coordinate transformation, that is the whole objective of making this coordinate transformation, right. So, the coordinate transformation has made this entire plate only having a vertical velocity and no horizontal velocity. That is the purpose of making that coordinate transformation. Okay. So, this one this is called as Reynolds equation in lubrication theory, a very famous equation. So, we will work out a problem where we will use this equation to solve the force between two plates. Okay. So, let us work out a problem. Let us say that there are two plates and there is a layer of viscous fluid in between these two, and the top plate is moved towards the y direction with a dimensional velocity, this one. Okay. So that this initial gap is increasing, initial gap at time equal to 0, h is equal to h0, but h is not a function of x. So question is, what is the force required to pull this, because if you are pulling this up, there will be a resistance in the fluid, which because of which you require a force to pull this, otherwise it does not spontaneously happen. So what is that force required? So that is a special case of this problem. So first of all, this h is not a function of x, right. Okay, first let us write this problem in a dimensional form, write this equation. So to write it in a dimensional form, I will not waste much of a time. So you will see that the only difference is a mu will appear here if you change these two dimensional variables. Okay. Just change all these to x dash, p to p dash, you will see just only one mu will appear, nothing else will change. So in the previous case, all the mu is absorbed in one of the scales, the velocity scale.
Initially, won't there be a 1 by v naught in v because it was non-dimensional as v?
Which one? 1 by v naught?
Y equal to x, v equal to del h by del t.
This is non-dimensional v naught. This is non-dimensional v naught. So this is non-dimensional. All these things without dash are non-dimensional. Any symbol without dash is non-dimensional. Okay. So this is and h not being a function of x, you can bring it out of the derivative. So h dash cube by 12 mu this velocity is constant, it is given that your objective is to pull the plate with a constant velocity, that is your objective. So you can write So, this is as good as 12 mu. What is H prime? H prime is right original H prime plus the change due to time because of the velocity, right. So, this is the instantaneous H prime, this is the H prime at time equal to 0. Okay. So, all these are not functions of x. So, you can take this as some k which is the function of time, but not x, right. So, you can integrate this with respect to x. We have used C1, C2, okay, K1 and okay. So, now the boundary condition is that we can set up a central axis and this we say as x equal to 0. This is L by 2 and this is another L by 2. Okay. So, at x equal to 0 you have because the pressure has to be symmetric with respect to it, here it is atmosphere, here it is atmosphere, right. So, if you put that then you have K1 equal to 0 and at x equal to L by 2 or minus L by 2 whatever pressure is, you can set it as atmospheric pressure, because if you set it as atmospheric pressure the remaining pressure will actually contribute to the force. Atmospheric pressure acts equally from all sides, so it does not contribute to the force. So, if you set this equal to 0 at x equal to L by 2 you have 0 is equal to k by 2 L by 2 square plus k2. So, k2 is minus k by 2 into L by 2 square. So, the pressure is equal to k by 2 into x square minus L by 2, this is the pressure distribution. Okay. So, we have only one more step left to calculate the force on the, say, force on the upper plate. F will be integral of this from x equal to minus L by 2 to L by 2 or 2 into 0 to L by 2 whatever. So, k by 2 into, so let us call it 2 into 0 to L by 2 because our domain is 0 to L by 2. So, k by 2 into 2 x square, this is x prime, x square is x prime cube by 3 minus L by 2 square to x. This is per unit width, right. Into width you can put if you want width of the plate. So, this is 0 to L by 2. So, this is k into, this is L cube by 24 minus L cube by this is 8, right, 2 into 2 into another 2. So, this will be, this is 3 minus 1 2, so minus k L cube by 12, right. So, one interesting thing is that we can see that the force is negative because this is all positive, right. So, the force is negative means when the plate is moving up there is something which is actually dragging it down, that is the physical meaning of this negative force. Now, in this way can you calculate the force unlimitedly? You cannot, because when this plate goes up and up and up there will be a situation when this H becomes comparable with L and then lubrication theory is no more valid. So, you have to, for solving any problem you have to keep this in mind, what are the assumptions of the theory, the basic thing has to be kept in mind. So, the basic thing is that H is much less than L. So, when this plate is moving up and up at some time H will become comparable with L and then this theory fails, this prediction of force does not work. On the other hand, the other limit is a very interesting limit, when the plate instead of moving up it comes down. So, when the plate is coming down, that is V0 prime is negative. So, if V0 prime is negative, this entire thing is negative and this negative into negative is positive. That means when the plate comes down there will be an upward force to resist that downward movement, and as time progresses, so in that case H will continuously decrease, right, because original H is H naught, then it will decrease, it will be H naught minus a positive number into time, right. So, there will be a time when the gap is very small, that is the two plates have almost touched each other and it varies with 1 by cube of that gap. Therefore, the force will be tremendously high. That is why you will find that if you have two plates you want to put an adhesive in between that two, when you approach the two plates you will feel a tremendously large resistance. That is, this is the physics of, these are very common day to day experiences. Take two glass plates and take a thin film of water, try to bring one of the plates to the other, you will see that you will face huge resistance when you come sufficiently close. Not only this one, but on the top of that intermolecular forces will also start acting, the van der Waals and the other forces will come into play when the plates are sufficiently close. So, this is actually a very interesting problem which is called as adhesive problem. So, you put an adhesive and bring the two surfaces very close to each other and see that in the limiting gap when the two plates have almost touched each other, it is virtually impossible to make those two touch. You cannot simply, because of the divergence of the force with 1 by h cube. Okay. So, we have discussed significantly about the lubrication theory and we have understood how pressure gets distributed in a system which is confined, but the confinement height can be a function of x and time. So far we have considered that the force that is acting is because of pressure distribution or shear, but there are many interesting problems in micro scale where the pressure distribution itself is generated because of the remarkable physics of surface tension, and from the next lecture we will start understanding how surface tension plays its role in microfluidics. Thank you.